Picture this. It's a hot summer day and you and your friends decide to have an epic water balloon fight in the park. To gain the upper hand, you want to perfect your water balloon launching skills. But instead of just tossing them straight, you aim to hit your friends behind the trees and the bushes. This is where the concept of angled projectiles comes into play. How do you determine the best angle and force to launch your balloon to hit your target? Here's the kind of physics you have to consider behind making the perfect throw to hit your friends. You have to consider the angle that you're launching at. You also must consider your initial velocity, the speed of which you initially throw the water balloon itself. You also have to consider the force of gravity pushing down on that water balloon. You must consider the maximum height, how high you actually want the ball to reach, and then also your range, so like your horizontal distance. By mastering those 5 main principles, you can predict the path of the water balloon and be way better at throwing water balloons than all your friends. So now that I've given a brief explanation and an example of angled projectiles, now I think it's a great time to dive a little bit deeper into the physics behind it to ensure that your water balloon will be able to hit all your friends and hit the mark. The actual definition of an angled projectile is any object that is launched into the air at an angle other than 90 degrees to the horizontal. The study of its motion involves analyzing both the horizontal and vertical components of its trajectory. With angled projectiles, there are multiple key concepts that are extremely important to understand before connecting all the dots. One concept is the initial velocity, which is the speed at which the projectile is initially launched at. It can be broken down into 2 components, the horizontal and the vertical. In order to calculate the horizontal component, it is the total velocity times cos theta. And the vertical velocity is the total velocity times sine theta. Another thing that's very important to look at is, just in general, the kind of horizontal motion and things to analyze horizontally. The horizontal component of velocity is something that maintains constant throughout the entire motion. So if you want to look at horizontally, the speed that's launched at initially is exactly the same, let's just say a couple meters in the air. The horizontal distance is called the range of the motion. So that's basically just start to finish horizontally how far that object moves, from where it is launched to where it lands right back on the ground. Also, it's very important to look at the vertical motion. The vertical motion is something that's affected by the acceleration due to gravity, negative 9.81 meters per second squared. That's the reason why the projectiles obviously come back to the ground, as gravity is what's pushing that downward force down. The vertical distance is something that can vary depending on the scenario. So the vertical distance could overall just be 0, and it could just be a flat surface. I could just be launching from one end of the hardwood floor to the other. But some scenarios, I could be launching it onto like a pad or, at the roof of a house, right? Which could be 10 or 20 meters up in the air. The vertical component of velocity is something that is not constant throughout the motion. When a full parabola is created, it is called a symmetrical example. And when doing the math for this, the v2y is actually considered to be at maximum height. So then that variable becomes 0. In a non-symmetrical example, for example, one where it would be launched onto the roof of a house, it cannot be assumed to be 0 as the v2y, rather just what it is near the end of the motion. Another variable that's very important to consider is the time of the flight. The time is an extremely important piece of information, as it shows just how long the motion lasted. It applies both to the horizontal and vertical components when you're doing your calculations mathematically. One fact that's actually very important to consider mathematically is that in symmetrical scenarios, when the v2y is considered to be at max height, the problem is essentially splits that parabola directly in half. So that means that when you calculate for time, you must actually double your answer. And then in your non-symmetrical scenarios, you don't have to do that, as that's just the entire motion. One of the best ways to understand how these variables interact is to actually do a problem itself to understand. So what we'll do is we'll use the same analogy that we used at the beginning of the video, that a water balloon is launched in this scenario at a 37-degree angle with a velocity of 20 meters per second. The best way to start off these problems is to organize your information. So your h v chart. That's how you do it. So right here. And your v1x is a value that we can get from this 37-degree angle and 20 meters per second. That turns out to be 20 meters per second times the cosine of 37, which comes out to equal 16 meters per second. So that's your v1x. That's a variable that we already know. And other than that, we know 0 variables from the horizontal side. For v1y, we can also get that variable from our 37-degree angle and 20 meters per second. So we end up doing 20 times the sine of 37, which comes out to be 12 meters per second. So that's how you break down those components that I was talking about earlier, your horizontal and your vertical. So that's how you break it down from your angle and your total or overall velocity, and break it down into these two components right here. Other variables that we know just based off the equation and the scenario of this being a symmetrical example, 9.81 meters per second squared is always going to be there in these scenarios no matter what. And then based off this, where it's a symmetrical example, we always must assume max height. So another variable that we can assume is our v2y, which in this scenario is just 0 meters per second. So a very, very common question that would be asked, especially with these scenarios, is to calculate the maximum height. So for these, you have to use kinematics generally. So for this scenario, we use v2y equals v1y squared plus 2ay multiplied by dy. And then once you derive everything and do your algebra to solve for your dy, turns out to be dy equals negative v1y squared divided by 2ay, which turns out to be negative 12 squared divided by 2 times negative 9.81. Once you do all your math there, that comes out to be 7.34 meters, which is your maximum height. And now another one that's also very common and very important to analyze when you're looking at the symmetrical examples is the time of travel. So for this, we calculated our vertical distance right here. So what we can say is we can use a kinematics equation from the variables that we already know. So you can say t equals v2y minus v1y divided by ay. And do the math. So 0 minus 12 divided by negative 9.81. So once you do that math there, you get 1.223 seconds. As many people, when they do this, they believe that this is the right answer initially. But where we assume that this is maximum height, that's essentially half the parabola. So when you draw your parabola, it looks like this, obviously. But in the scenario where we have a symmetrical, we assume that it stops right here at that little line right there. So in order to take your time here, the time up equals time down. So you actually must take this and multiply it by 2. So when you do that, that gives you, rounded, 2.45 seconds. And that's your answer for your total time of travel. So doing just a simple problem like this ties all the variables together and really shows how they interact. One very interesting thing about angled projectiles is that many of us use it in our day-to-day lives without even really recognizing it. For example, if I'm playing basketball, in order to get that ball into the hoop, I have to analyze all of those variables almost subconsciously in order for me to try to hit the best shot possible and get that basketball into the net. Another very interesting application of projectile motion is actually how the military uses it. Even now sometimes, but more so I'm kind of referencing the past. A couple hundred years ago, when the military would launch off cannons, they would have to use all of these principles in order to get that cannonball to land where they want it to. Generally, they were aware of the force that they need to use, also the angle to put it at, so that it could go to the range and the distance that they thought that it needed to go. And having a knowledge of this give a huge advantage in battle. Okay, so now I'm going to give a demonstration of an angled projectile and how changing the angle actually affects the range of the projectile. So what I'm going to do is I'm going to take this little plastic ball here and I'm going to launch it up the hallway, measure the angle that I actually launch it at, keep everything as consistent as possible, but still while estimating, just to give an approximation and show how changing the angle does actually affect the range. Okay, so that one there was launched at a 20-degree angle, and it landed approximately just at that little red slip by this book. So I'm just going to lay this little marker here just to show where that landed. Now I'm going to try it at a 45-degree angle. Okay, so that one there, the 45 degrees, you can see where the 20-degree one went. The 45 degrees went a little bit further, which in theory it should. So that's correct there, and that's where that one goes. So a noticeable change there in the range. Now I'll be doing a launch at a 70-degree angle. So that test launch there, it landed on nearly the exact same spot here as the green, which is how, in theory, the experiment should go. As 45 degrees is supposed to give you the longest range, and both these other angles I did were about 25 degrees away from 45, so the fact they landed on the same spot makes perfect sense. And this just shows and proves the point that angle projectiles do work in practice. In summary, angle projectiles are a fundamental concept in physics that explain simply how objects move when they're launched at an angle. By understanding the horizontal and vertical components of motion, we can predict the path, height, and the distance of the projectile. This knowledge is crucial in various real-world applications, such as, talked about in this video, sports, engineering, military, and many, many other things. Measuring this concept not only enhances our problem-solving skills, but also deepens our appreciations for the laws of physics that govern everyday life and advanced technologies. So now, based upon the knowledge that you've gained throughout this video, now you may have a better chance at least being more intellectually sound at predicting how you can best hit your friends with a water balloon.